Have you ever stopped to think about the magic trick your computer pulls off every single second of every day? We're about to pull back the curtain on that trick, multitasking, and really understand the powerful idea that lets your computer juggle literally everything you throw at it. I mean, seriously, think about it. You've got one computer with maybe a handful of CPU cores, but right now you could be running dozens of different programs without a hitch. How is that even possible? It feels like magic, but it's actually a really elegant solution to a super complex problem. And that right there is the fundamental challenge. This is the core problem that every modern operating system, I don't care if it's Windows, Mac OS, Linux, you name it, is built to solve. How do you take one physical CPU, or a few of them, and create this incredible illusion that you have a nearly endless supply of them, one for every single app you want to run? So to figure that out, here's the game plan. First, we are going to meet the absolute star of the show, the process. Then we'll follow a process through its surprisingly dramatic life. After that, we'll uncover the OS's master plan for keeping all this organized. And finally, we'll tie it all back to why this is the bedrock of pretty much everything you do on a computer. Okay, let's dive right in. To make all this multitasking work, the operating system needs a way to think about and manage a running program. And that central idea, that core abstraction, is something called the process. So what on earth is a process? Well, informally, it's just a program in action. Think about an app icon sitting on your desktop. That's not the program, not really. It's just a bunch of lifeless instructions sitting on your hard drive. But the moment you double-click it, the operating system swoops in, breathes life into it, and transforms it into an active, running process. The OS pulls off this incredible trick using a concept called CPU virtualization. It sounds fancy, but the idea is simple. It runs one process for a tiny, tiny fraction of a second. Then it stops it, saves its exact state, and then runs another one. By switching back and forth between all these processes incredibly fast, it creates that powerful illusion that they're all running at the same time. And this slide really nails a key difference in how resources get shared. For the CPU, the OS uses time sharing. Every process gets a little slice of the processor's time. This is completely different from space sharing, which is how your hard drive works. A file gets its own dedicated physical space and just holds onto it. So just remember this. The CPU is shared by time, the disk is shared by space. It's a critical distinction. So when the OS looks at a process, what does it actually see? It sees what's called its machine state. Think of it like a chef's workstation. The memory, or its address space, that's the entire pantry of ingredients the chef is allowed to use. The CPU's registers are like the tiny prep bowls right on the counter holding just the ingredients for the very next step. They're super fast. And then you have the program counter. This is crucial. It's like the chef's finger pointing to the exact instruction in the recipe book they need to do next. Those things together are a complete snapshot of the process at any given instant. Now, to manage all this, operating system designers use a really brilliant principle. They separate mechanism from policy. The mechanism is the how. How do you physically stop one process, save all its stuff, and start another one? The policy is the which. Which of the dozens of waiting processes should get to run next? By separating these two, you get a system that's way more flexible. All right, now let's see how all these pieces come together. A process isn't just static, you know? Its state is constantly changing, moving from one state to another based on what it's doing and what the OS tells it to do. At any given moment, a process is in one of three key states. Running is the obvious one. It's actually using the CPU right now. Ready means it's totally prepared to run, it has everything it needs, but it's just waiting in line for its turn. And blocked means it's stuck. It can't run because it's waiting for something slow to happen, like for a file to finish downloading or for data to come back from a hard drive. And this diagram shows that flow perfectly. The OS schedules a process, moving it from the ready state to the running state. If its time is up, the OS can deschedule it, which just sends it back to the ready queue. Now, if a running process needs to do something slow, like read a file, we call that I/O. It moves over to the blocked state. Once that slow thing is finished, it moves back to ready, waiting for another shot at the CPU. Let's walk through this with a real example. Just follow the table. At the start, process 0 is running along, but at times 3, it needs to read from the disk, so it becomes blocked. The OS is smart though. It doesn't waste a single moment. It immediately switches to process 1, which now gets to run. Now pay attention to time 7. Process 0's disk read is done, and it moves to the ready state. But notice, the OS lets process 1 keep running until it's finished. Only then does it give the CPU back to process 0. And that decision right there, that's a classic systems design question. This is the exact kind of problem you'd get in an interview at a big tech company. The OS could have immediately interrupted process 1 and switched back to process 0, but it didn't. Why? Is it better to avoid the cost of switching back and forth, or is it better to prioritize the process that just became unblocked? This is a real-world policy trade-off, and honestly, there's no single right answer. So how in the world does the operating system keep all this straight? How does it remember the state, the registers, and everything else for hundreds of processes at once? Well, it has a master plan, and it's all built on a few key data structures. The absolute cornerstone of this plan is the Process Control Block, or PCB. The easiest way to think about it is like an ID card for each and every process. It's just a data structure where the OS stores everything it needs to know: the process ID, its current state, where it saved the registers, you name it. And all these little ID cards are kept together in a big master process list. And this isn't just some abstract idea. This right here, this is what a PCB actually looks like in real code. This is from a teaching operating system, and this struct proc is that ID card we were just talking about. Even if you don't read C, you can probably spot the things we've been discussing. There's the state of the process, its PID or process ID, and that context thing, that's where it stores all those CPU registers. This is where the theory hits the code. The OS also gives us a toolkit, an API, to manage these processes ourselves. When you launch an app, you're basically using a create command. When you have to force quit a program that's frozen, you're yelling destroy. These are the basic commands that give us and other programs control over the entire process lifecycle. Okay, we've gone from this high-level grand illusion all the way down into the weeds of the code. So let's pull back up and talk about why this concept is so incredibly important. I love this quote. It's so simple. The definition of a process is a running program. This comes from a paper written way back in 1965 from Multics, which was a predecessor to Unix. This just goes to show you that the process isn't some hot new idea. It's a foundational concept that has been powering computing for over half a century. And that's really the main takeaway here. The process is the fundamental abstraction that makes everything we do on a modern computer possible. Without it, you couldn't listen to music while you browse the web. You couldn't do anything, really. It's that simple, and it's that important. And once you understand this, so many of those little computer mysteries start to make sense. Why does your computer get so slow when you open a ton of apps? Well, it's because the CPU is spending all its time just switching between a huge line of ready processes. How does an app stay responsive even when it's doing heavy work? Because it can put the long, slow tasks in a blocked state while the user interface keeps running. It all comes back to this. So, our journey today has taken us all the way from a simple illusion of doing everything at once down to the complex data structures that make that illusion a reality. The process truly is the bedrock of what a computer does. And so, I'll leave you with this one final thought. This idea, the process, has dominated computing for over 50 years. That is an eternity in technology. As we move into this new era of massive distributed systems and cloud computing, what comes next? What new abstraction, if anything, do you think will one day replace the process? Thanks for watching.